Hey, good day, my students. Welcome to the Google Classroom, a simple way of delivering classes together with you. Even though we are not in contact, we are not seeing each other, but minded, we are still with us. And I assume you are in my front, and I'm in your front too. So we discussed on radioactivity last classes before the COVID-19 pandemic, and a lot of concepts were explained. So we have to revise it up and up before we continue with the next part of it. So what we discussed on by then was radioactivity, and we defined radioactivity as the spontaneous decay or disintegrations of radioactive elements by emitting energies as particles. The energies or the particles or the radiations emitted by radioactive substances after decaying are three. Number one is alpha particle, number two is beta particle, and number three is gamma particle. In some textbook, they are called decays, radioactive decays, or radioactive byproducts. Whatever it's called, and it's the same still. So it is alpha particle as a positive particle, and the beta particle as the negative particle, and the gamma, which is a neutral. All of them are radiations emitted by radioactive substances immediately after decay. So the alpha particle is also a helium nuclide, while a beta particle is electron nuclear also, while the gamma is neutron. So that's what they do. In a practical aspect, we have a block. We have just an aluminum block. You now put your target here. You put your target here as thorium, boron, thorium, radon, all of them can be served as a radioactive substance. One they are put in here, after some time they will decay and start emitting rays. And these rays are in form of this, and this is called an alpha particle, while this one is a beta particle, while this one is a gamma particle. The screen here, all of them will lie on here. So now what we have, why this one deflected here? Why alpha particle deflected to the down and the beta particle deflected upward here? The reason why is because once there is negative charge back here, when there is negative charge, we know alpha particle as positive will definitely look for a way to attract by the negative pigment here. So alpha is positively charged, so it will deflect it to the negative conductor. So in this part, why beta deflected there is because there is a positive conductor here. There is a positive conductor. Once there is a positive conductor, so beta particle is negative, they will be attracted by the positive charge conductors toward that side, while gamma has no charge. It's a neutral particle, so it has nowhere to bend into. It will go straight direct to the screen. So that's how the experimental demonstrations of the radioactivity is. There are types of radioactivities. Number one, we have artificial radioactivity, and number two, we have natural radioactivity. When I say a natural radioactivity, is the natural decay of substances without applications of any other substance to pastor the decay or to stop the decay. So they decay, they disintegrate naturally. Once you keep them for some certain time, they will exercise energy, and that energy will make them to decay and emit those rays as gamma, beta, and alpha. That is the alpha particle, the gamma particle, and the beta particle will be decayed naturally without applications of anything. So that's what is called a natural radioactivity. So we have an artificial radioactivity where some substances will be used to decompose another substance. So in that case, the radioactivity or the decay or the disintegration can never occur naturally. It can occur only by the applications of other substances. So that's what is called artificial radioactivity. Now, what we have again is what is called a half-life of radioactivity. A half-life of radioactivity is the minimum time taken for half of a substance to decay and emit those particles. You hope you understand. Assuming you have thorium, you have a thorium with 20 grams of thorium. The half-life of thorium now is the time taken for 10 grams of thorium to decay is what is called the half-life of thorium. Now, assuming if the half-life of thorium is 1 year, if the half-life of thorium is just 1 year, meaning after 1 year, 20 gram, or after 1 year, 10 gram of thorium will decay instead of 20. So after 1 year, 10 gram of this thorium of 20 gram will decay and leave only 10. So after 1 year, 10 gram will remain. The other 10 will go off as decay particles, emitting those particles of alpha, beta, and gamma. So that's what is called a natural. Immediately you keep this thorium in a place for some certain time. Once it reaches 1 year, therefore half of this 20 will decay and leave half, because the half-life is 1 year. If the half-life of thorium is 2 years, meaning after 2 years, whether you put it in a place, whether you put it in a dark place or in a space where there is air or anything, once it reaches 2 years, therefore half of this 20 will decay. Why? Because the half-life of thorium is 2 years. If the half-life of thorium is 3 years, meaning after 3 years, 10 gram of this thorium will go up as decayed, while other 10 will remain in it. So that's what is called a half-life. There is expression that somebody or one can use to find the half-life of a given substance. Like the formula is T equals to 0.693 divided by lambda. You understand? We call this lambda to be a decay constant. Decay constant. It is called a decay constant. It is called a decay constant. While this T is called the half-life. The half-life of the radioactive substance. While this is a numeric values gotten by integration and differentiation, we're able to reach here. So this is the half-life of radioactive substance. T equal to 0.693 over lambda, while lambda is called the decay constant, while T is the half-life. While this decay constant is usually given, it's usually given in every calculation or in every question given to you. It's going to be given, then you ask to find the T. Or sometimes they'll ask you to find the decay constant while the half-life will be given. How do you understand? Like, example, the half-life of thorium T is 2 years. Find the decay constant of the thorium. What you do is just use this formula. T equals 0.693 divided by lambda. And this is equals to, or let me see, you now substitute the T, and T is 2 years, put 2, equal to 0.693 divided by lambda. Divide both sides by 1 here, multiply, cross multiply everywhere. 2 times lambda is just 2 lambda equals to 1 times 6.93. It is something as 0.693. Then divide both sides by 2. 2 goes to 2 here, we have lambda to be equals to 2 here, 1, we have 0.3465. This is the decay constant. So simple. Since you know the formula will be enough for you to calculate whatever you want. My student, please, my advice here is, I've been telling you this, please. Once you are given an expression or a formula that one can use to calculate something or a quantity, that formula means a lot. You have to hold it on and on. It's very, very important. So this is the formula that one can use to calculate the half-life of radioactive substances. If it's not done manually, it can be done manually. Sometimes they'll ask you to calculate the number of grams remain after 5 years of a given substance, if the half-life is just 2 or some certain years. So this is it. If you refer back to the textbook, some things like this have said, and I'm going to write it as a note and give you. I think I've written something like that for you. So it's like we are divided now. We are now looking at the types of radioactivity, like I said, transformations of elements under radioactivity. As radioactivities as an element, they always yield another substance whenever they decay. Apart from the alpha, the beta, and the gamma particles emitted after disintegration or after decaying, they emitted another substances also. Different properties and characteristics, everything. So that is it. And the elements will be yielded may not be necessary with the father or with the mother element. We have types of transformation, which is natural transformation and artificial transformation. In natural transformation, we don't need any other substance to bombard the initial substance. No. It is the initial substance will exercise energy again or will be bombarded naturally and yield some particles, which is called alpha particles or beta or gamma particle, and yield energy and some other substances. Like in the first example I have, we have radon 226 with atomic number 88, will decay and give alpha particles with helium nuclei, which is 4 and 2 in the atomic number, plus radon, and radon is 222, radon 222, and 82 as atomic, and 86 at atomic number as atomic number, plus energy. Look at it here. We have radion, we have 226 mass number and 88 atomic number. After some times, this very element or this very radioactive substance will decay. After decaying, it will emit alpha particle. It will emit alpha particle, which is called a helium nuclei, as 2 atomic number and 4 mass number. This is not the actual element emitted, no. It is a particle, which is called an alpha particle, produced after decaying. Now, what is the result, or what is the residues? What remains after this decay? The residues is radon. It's radon 222 with atomic number 86 plus energy. All of you will confuse on how this goes. In every natural transformation, assuming you have a substance X with mass number A and atomic number Z. Once it decays, it will produce an alpha particle. After producing alpha particle with mass number 4 and atomic number 2, it will produce another substance Y. And this substance, this very substance, will have a mass number, A minus the mass number of the helium, which is 4. And the atomic number will be Z, the atomic number of the initial minus the atomic number of the alpha particle, which is 2. Now, plus energy. And do you know this energy has formula mc square? This energy is mc square emitted. This energy is in form of what? Mc square, mass times speed of light here, square. So that's it. So this is the what? The natural transformation, which is called an alpha transformation. This is natural alpha transformation. So in this case, using this skeleton, you can be able to know why this one decay emits this, and this. Now, radon has 226 as mass number, 88 as atomic number, decays, produce alpha particle with mass number 4 and atomic number 2 as helium nuclei. This is the symbol of alpha particle as helium nuclei. Helium and alpha particle are all the same. Helium has 4 as mass number, 2 as atomic number. Also, alpha particles has 4 as mass number and 2 as atomic number. Then plus another substance which is called the residues or byproduct. This element transforms to this element. This is radium. This is radon, radium, and this is one. This one is radon. Radon and radium. So this one produces this with mass number 22 and atomic number 86. How? By saying 226 minus 4 making 222. Then 88 minus 2 making 86 plus energy released. Plus energy released. In artificial bombardment, it releases energy. It releases energy, and that energy is in form of formula mc squared. That is delta E equals to mc squared. That is the energy emitted naturally. So you may think on where we get this element and this element. If you are given this, to find this, you are to think which among the radioactive substances that can be gotten when you subtract 4 from its main mass number. Then think of the element that has very mass number like that. Assuming if here is 8. Now, after you remove this 4, after you remove 4 from 8 here, it becomes 4. Now you think of a substance that has mass number 224. Whatever that substance is what you are going to put here. And if it has 224, definitely you find out that it has 86 as atomic number. So that's how you think and put the answers right. You are SS3, you make sure they're not, all these are not something hard. you can refer back to so many textbooks and get relevant information on this radioactivity. So that is